We'll wait for others to join, then we'll start in few minutes. All right. So welcome back everyone to week 4 tutorial of the course Fluid Mechanics. I hope everyone is regular to the lecture videos by the professor on the NPTL portal, as well as you all are completing your assignments on time. So in the last tutorial, we finished up with the surface tension and capillarity concept. And in today's session, we will start with the pressure measurement. Let me share my screen. Okay, I think my screen is visible now. So let us start with the topic pressure measurement. So we need to uh, measure the pressure basically. So before measuring the pressure, let us understand what pressure actually is. So pressure is nothing but a normal force per unit area in the fluid. Okay. Pressure is always acting in the fluid. Okay. Just hold on. Yeah. So it is always acting in the fluid. And as per the Pascal's law, pressure has no direction. Okay. So it's a scalar quantity. And pressure has infinite directions at rest condition at a particular point. Okay. At a particular point. I hope I'm audible clearly, right? Oh, great. Okay. So also pressure is compressive in nature and pressure force always acts perpendicular to the surface area. That means it is acting, it is a normal force of corresponding area which defines the pressure. Let me first of all write all these points. So let's start with pressure. So first point states that it is a normal force per unit area in the fluid. Okay. To emphasize this point that it's always in the fluid, not in solids. There we measure stresses. And as per the Pascal's law, as per the Pascal's, pressure has no direction.
Power on. Bluetooth mode.
Yes, Afroz, any doubt? That is, it is a scalar quantity. That also means that pressure has infinite directions. That is, pressure has
You are now connected.
infinite directions. Infinite directions at, and this is only possible at a rest condition at a particular point. Rest condition at a point. So to highlight that, at rest conditions, very important. All right. Also, pressure is compressive in nature. Alam, do you have any doubts? If not, can you please mute yourself?
No, sir.
Yeah, ask me. Okay, no problem.
No, sir. No,
Can you
no,
please,
doctor.
can you please mute yourself then?
Yes.
It is compressive in nature. Okay. Also, pressure force always acts perpendicular to the surface area. Pressure force, I'm not saying pressure. Pressure has no direction or infinitely acting at a point in rest condition. But the force, because of the pressure, always act perpendicular to the surface area. Pressure forces is always perpendicular to the surface area. That is normal force of corresponding area defines pressure. That is normal force of corresponding area, whatever area you choose, on that corresponding to that area, uh, pressure is defines the pressure is defined. What do I mean by that? Let us understand this thing. Also, to okay, so first of all, let's understand. So suppose if I have a plate like this, I have an area, complete plate like this. Let me just make it a bit down. Okay, so this is a plate with the area A, complete area A. Suppose I take a small elemental area in this much. Okay, so this has area dA, small elemental area dA. Okay, now we know that at this element, small element or a point, its the element is like a point. Pressure is acting in all directions. This is pressure, not pressure force. Suppose like this. In all direction, at this point, pressure is acting P. Okay, P, 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 and so on. Okay, but the pressure force, because of the combination of all these pressure at that point, the force will always act perpendicular to that area. So it will be perpendicular like this, and this is F dF, because it's a small dA element, so pressure will be dF, and it is in normal direction, dFn, dFn. Okay, so what we can say, pressure is normal force per unit area in the fluid. So pressure will define pressure P is nothing but limit of dA approaching to 0, because it's a very small element. It will be pressure force, that is normal force, per unit area, that is area. Okay, dFn by dF. So it's basically d of Fn by, okay, d of Fn by d of E. And unit is pascals, Newton per meter square, or Newton per meter square. Unit is Pascal or Newton per meter square, because force has a unit of Newton, area has a unit of meter square, Newton per meter square. Okay, this was a scenario where pressure was acting at a point and we have considered normal force. Suppose I have a scenario like this. So I have a plate like this. Okay, I'm now showing, first was an isometric view, now I'm showing you the front view of the plate. And again, pressure is acting. Suppose at this point, pressure is acting, pressure is acting and acting, right? EP. And again, we have a normal force, d of Fn. Okay. So as I've said, pressure is always perpendicular to the surface area. We have seen this from here. But also, another statement I have said that normal force of corresponding area defines the pressure. So normal force was this in this case, and is this in this case, defines the pressure. But suppose if I take the component of this normal force, suppose I take a component of this normal force. So this was a very small element area like this. Okay, small element area. So instead of taking DFN, I take component of DFN. Goes like this. And it is at an angle of theta, suppose. So this will be DFN, how much? Of DFN, not DFN, D of DF theta at a particular angle theta. DF theta. Now pressure will be defined normal force corresponding to that area. So now I cannot take this area. This area I cannot take, this small element. Now I have to take the area in a direction perpendicular to that of this force. Okay. So what will be my area now acting? It will be a area like this. Okay. I should make again. I guess I made a big. This will be the rotated area. And again, it is at dA of theta. This is dA of theta. And this was dA of n. okay, or dA, not n, dA of theta and dA. So now the pressure will be, actually it is a point which is acted by a lot of pressures, P, and as I've said, pressure is a compressive in nature. Okay, compressive in nature. So it is nothing but pressure is nothing but negative of stress at rest. At rest. So that means there is no shear stress here. Okay, there is no shear stress here at this point. So what can I write here? Pressure of theta. Now here, pressure of theta we have to get. So because we are getting force of theta which is acting on a area dA theta. So pressure will not be P. This time pressure will be P of theta. So P of theta will be limit again, or you can directly write instead of limit dF theta by dA of theta. Okay, we know that dF theta is nothing but Pfn cos theta, and dA theta is nothing but dA cos theta. Right? So put these values, dFn cos theta and dA cos theta. So this cos theta cancels out again. Therefore, your P of theta is nothing but, again it comes out to be dFn by d of A, and it is nothing but P only. It is only nothing but P. This and this value comes out again same. So it doesn't matter you are taking the component of the normal force and then taking the area perpendicular to the component of the normal force. Pressure is always force per unit area. Force per unit area. And pressure is always a compressive in nature. Pressure is always compressive in nature. So if I say that you draw a Mohr circle of the pressure, what will it look like? So in strength of material course, you might have drawn your Mohr circles. Okay. So Mohr circle is for this scenario, this scenario, this scenario, where pressure is acting and it is compressive in nature. So the Mohr circle plot is the between shear stress and normal stress. Okay, shear stress and normal stress. And first of all, it is compressive in nature, so it will be negative value. Here, shear stress is zero, though no shear is acting over this. Okay, so no shear is acting. So Mohr circle will be negative value and no shear. Shear stress is zero, and it is a negative value that is nothing but equal to P. P is your pressure. Okay. So finally, your Mohr circle is just a point having a pressure P, and it is a negative value, negative of sigma, negative of sigma. Okay. This is Mohr circle is a point. Basically, I'll write here Mohr circle is a point. Okay. All right. So I guess both the statements are crystal clear now. Now we will think about a scenario where surface is said to be a free surface, and it is said a surface said to be a free surface when there is no shear stress acting or there is no force over that surface. Okay, a surface is said to be free surface if there is no shear stress or force, shear stress or shear force over that surface. Let me write like this. Okay, so suppose again I have a scenario like I have a plate like this. Okay, and there is a force acting like this in this direction. Suppose F. So again, it can be bifurcated into two components, vertical and horizontal. So what will vertical component look like this? That is F, or suppose this is the angle theta from the plate of this force. Angle theta is like this. Okay. So this is F cos theta, and this will be F, sorry, F sine theta. My bad. F sine theta, F cos theta. Okay. So this is your normal force, and this is your shear force parallel to the surface. We have seen this in the first lecture. Okay. So that, and F is not zero. F is non-zero force which is acting on the surface. All right. So Fs is F cos theta. Okay. Suppose if theta is 90 degrees, theta is 90 degrees, because currently there is a shear force, there is a normal force because of this. But if theta is 90 degrees, that means the force acting is perpendicular. Then Fs is F cos 90, that is 0. That is 0. So in this scenario, where Fs is 0, but and Fn will be how much? F sine 90, that is F. In this scenario, when the fluid is at rest, then shear stress or force Fs is 0, and that kind of surface is called as a free surface. This is the scenario for this. So in this, we can understand that at rest, Fs 0, this implies shear stress is 0. So free surface, this is free surface. Let me write here. For this condition. Okay, for this condition. And also a point to remember that free surface will only form when the pressure above the surface is greater than the vapor pressure of the fluid. Otherwise, there won't be any free surface. Okay, and shear stress should be 0. If it's a free, then the liquid will evaporate basically. So pressure cannot above this means above if this is a liquid. So here the pressure should be greater than P vapor always, whatever vapor pressure of that liquid is. Okay. All right. Otherwise, it will start evaporating. Okay. Any doubts still here to anyone? Yes or no? Any doubts? Any understanding? Any of these points? All right. I think we have understood what pressure basically is. Now, what pressure can do? Let us see a scenario. So suppose I have a scenario like this. Okay. So a system like this, there are two cylinders, or you can say pistons. Let me use another color. Or a platform, you can say. And here also at the same level, I have a platform like this. Okay. So suppose you have put a weight here, that is W. A W weight you have put here, which is acting downwards. You can have a car, tire, or any machine, anything can it be. Okay. And this hole is filled with liquid, whatever fluid it can have. Okay. Now what you do, what will happen here is that if you push the right hand side lever with the force F, or piston with the force F, if you push this, so what's going to happen? There are some water molecules here, or liquid molecules. I should not specify the liquid. So some liquid molecules are here. They are transferring the pressure. Eventually, a pressure is going to act now. Because of the force, pressure is going to act. And the pressure is always acting at a point in infinite directions. So this pressure is going to transfer from this point. Equally, it's going to transfer everywhere. Suppose here also, here also, here also. Okay, all the points have the same equal pressure, or here also the pressure is. But what you observe here is that here the liquid molecules are more at this surface, okay, compared to the right side when you push this, okay. And here force is nothing but pressure into area, okay, pressure into area, or pressure, you can say that force upon area, okay. I can write it in that sense. So here pressure is nothing but force per unit area on this area. It's always acting normal to the surface, as we know. Okay. So when you push this plunger, so it is going to transfer the pressure, and the pressure is gonna be same. And the object on the left hand side, a heavier object, is gonna lift up. Okay, is gonna lift up because of the presence of lot of you can say molecules of the water. So net effect is Fp acting. Okay, Fp is acting. So Fp is balanced by, to be in equilibrium situation, Fp is balanced by the weight. Pressure force is balanced by weight. What is pressure force? Pressure force is pressure into area. From here, pressure force is pressure into area, and weight is W only. Okay, weight is W. Now, now we need to see what is pressure. Pressure is again force by area. We can write in this term force by. So point to note here, you might get confused, is that at this point area is A, at the area of this side of the cylinder is A, the area of this side of cylinder is, or piston is, small a. Okay, is small a. So that's why we are balancing on this side. So force is pressure into capital A. So I'll write here as well to be small a. Okay, F by small a. Correct. And pressure again can be written as force per unit small area on the right hand side. Okay, into area is nothing but W. So from here you can get the ratio of what? W is nothing but how much? W by F. The ratio of W by F is nothing but area capital A by small a. Capital A by small a. Now we know that since capital A is greater than small a, that means capital A is greater than small a, W weight is always going to be greater than F, the force which you apply. So weight of the object is greater than the force which you apply. Okay. So what does we say this? This is a scenario of a hydraulic lift, that with less amount of force, you can lift up very heavy objects as well. So this setup is nothing but a hydraulic lift. Hydraulic lift. Okay. And the fluid here is incompressible. Mark my points. The fluid is incompressible fluid. Okay. Incompressible fluid. So what we can say here is that therefore in less force effect, for less force lift has more effect. Okay, so for less amount of pressure, you can lift up. That's what happened in hydraulic jack. So if your vehicle tires get puncture in the sideways of the road, so you take out from your backside of your car the hydraulic jack, and you just push some with the lever, and the tire gets the weight of the tire gets uh, lifted up. Okay, with less amount of force. Okay. So, as per Pascal's law, the increased pressure in static fluid is delivered in all the directions. So, whatever pressure has been increased, it is delivered same in all the direction by same intensity. Okay, that's why it has traveled here. All right. Also, what you can say, if you press this, that is gonna lift up. So, scenario like this, I will make this again. Okay. So, suppose you have pushed this and it has got lifted up, right? So from the reference level, suppose from this reference level, earlier it was at, so I should have made like this. I'll make again. From here to here, this you have pushed it. Okay. And I should make a bit more that I can. And from here, the weight has been pushed up. Okay. So suppose this has traveled delta x, or x, you can say x has been displayed. And from this point, this has risen up by y. So I'll just make it. So this has risen up by y. Okay. All right. So what has happened actually? The volume, initial volume and final volume is going to be same, or left hand side, both left hand side. So volume of W is equal to volume displaced by F. Okay. So here W was acting, here F is acting. So volume here is, suppose this is an area small a and this is an area capital A. So it is of W, it is A into Y, and it is A into small x. Okay, so Y is nothing but AX by capital A. AX by capital A. So if I say what is work done by F, the force F. So work done by F is nothing but WF is force into displacement, F into X. And work done by weight W side piston, it is W of W is nothing but force is how much? F again, or weight again, F is equal to weight into displacement Y. And Y is nothing but, if you put it here, is nothing but W AX by A. Okay. And W is nothing but force. Okay. Balanced by the force. Okay. which is again going to come out to be a same value. Force into area into x by a. Okay, so that is force. All right, because we have calculated this from here. If you observe, work W is nothing but FA by A. Sorry, my bad. I'll write again. F W is since F A by small a into A x by A. So this cancel out with this cancel out with this. This is F into x. That is same force has been done. Since W is nothing but F A by from above. So both the displaced work done is same from both the sides. So energy is converted and conserved. All right. So energy is so work is form of energy only, and heat is also form of energy, but because of the temperature difference. Therefore, I can say energy is also conserved. Okay. All right. Now let's see the validity of the Pascal's law. Validity of Pascal's law. So it is valid for both viscous, non-viscous. Just hold on, please. Yeah. So I was saying it is valid for viscous, non-viscous, compressible, incompressible fluids. But the point to note here is that the fluid must be at rest. Then only it will be valid. The Pascal's law. That is, pressure is equal in all the directions. Okay. It is acting and of same intensity in all the directions. And a fluid in a container, if I have a scenario like fluid in a container, which is moving with constant velocity or a uniform acceleration or uniform angular velocity then also this there is a validity of the Pascal's. Also, ideal fluids which have we have seen what different kind of fluids. Ideal fluids which have zero viscosity, that means zero shear stress. Then also it can have the validity. Okay. Okay. So let me write first point here that it is valid for viscous, non-viscous, compressible, incompressible, incompressible fluids. But point to note here is that fluid must be at rest. Okay, so noted. Must be at rest. So fluid in a container where container is moving with constant velocity or uniform acceleration That means velocity is increasing or uniform angular velocity. Let us see these scenarios one by one. So first scenario, let us see, is it valid or not? So I have a scenario like this. I have a beaker. I have wheels. There is a fluid in layers. And this beaker is moving with constant velocity and acceleration is zero. That means acceleration is zero. And this is your datum or reference. Okay. This is a symbol for this. This is a datum or reference. So at a particular layer, suppose I choose this layer. I've chosen this layer. Here, which is at height h. Height h. Height h. All these points have same pressure P. All these points at this layer will have same pressure. So it is valid at this position. Okay. Fluid is at rest for this layer. Okay. With respect to container, fluid is at rest with respect to container. But as I increase, go in depth from starting from this point to this point, the pressure is going to increase. But for individual layer, the pressure will be same for them. Okay. Why? Because fluid is at rest with respect to the container at that side. So here I'll draw the plot of the pressure. It will look like this. Air pressure will be some another value, higher value. Here some another value. Here some another value, and so on it goes. Okay. So what can I write here? Fluid is at rest with respect to container. Okay. All right. Next scenario where your fluid is moving with constant acceleration. Let us see. So if a fluid is moving at constant acceleration, so velocity is increasing eventually. That means A of in the x direction is constant. That is, velocity is increasing. So what will happen to the fluid layer? If you sense it physically, the fluid is gonna go up like this. Okay. So if I say between these, suppose this is H1, okay, from the reference it is H2, okay. If I go like this, so this is your reference line. Here also this was your reference line. Okay, reference line. From the reference lines at a height H1 and H2, okay, the pressure is again gonna be same for that layer, but it's gonna increase correspondingly. Again, fluid is at rest with respect to container after some time. Initially there will be some jerks, but as soon as it achieves a steady state, okay, then fluid will be at rest. So these are constant pressure lines eventually. These are your constant for that line, constant pressure lines. The pressure is going to be same for that particular line. So suppose again I'll make a graph out of it. So it will again look something like this one. But here suppose here pressure is P1, here pressure is P2, P3, and so on. Okay. So fluid is at rest. With respect to container, but after some time point to note here. Because it's gonna start with acceleration 0 and it's gonna achieve a constant acceleration. Okay. That's when steady state is reached. All right, done. Another scenario is that when you have a cylinder, okay, and you have rotated. First, let's see, a cylinder is kept and it is not, nothing is happening. Suppose like this. A cylinder is there, fluid is kept here. Suppose we take this as the reference line. Okay. So I'll write RL for this. So this is your reference lines once again. So suppose we take some points below this. At this point, this point, this point, which is at height h, the pressure is going to be same. Pressure is going to be P, P, P all the time. Okay. So pressure is not function with the radial position. Point to note here is that pressure is not the function of a radius. Okay. This is your position. This is your radial position of that cylinder. Now, if I rotate the cylinder, what's going to happen? So again, I have a cylinder like this. But what I'm going to do is that rotate with an angular velocity omega, constant angular velocity. So fluid is also going to rotate. Fluid is also going to rotate here. Okay. So again, these all are constant pressure lines. Constant pressure. Sorry. Constant pressure lines. Constant pressure lines. So fluid is again at rest with respect to container after achieving some time or steady state. But here pressure is a function of the radius. Because here with radial direction, pressure is going to change because heights are changing. So pressure is not going to be same this time. Okay. Pressure will be I should draw here. Okay. So these all are constant radial line, but with the radius, constant pressure line. But if you see, the pressure is gonna change depending on the radius. Constant pressure lines, but okay. So P is function of radius, and fluid is at rest again. With respect to container, after some time. Okay, point to note here after some time. Okay. Another point is that ideal fluid where viscosity is 0, that means shear stress is 0. So outside the boundary layer of the fluid will be ideal flow. Okay. So for idle, I'll write here. Idle fluid is nothing but zero viscosity, that is zero shear stress. So if I have a plate, the fluid will be in layers, parallel layers. Okay, there won't be formation of any boundary layer. So this is flowing with a velocity of u infinity, and at point 1 and point 2, suppose this is a section 1 and this is a section 2, hydrostatic law can be applied. That means energy is conserved because ideal fluid flow is there. There is no viscosity. Okay. So this is also traveling with velocity u infinity only. Okay, u infinity. So ideal fluid flow hydrostatic law can be applied. And energy is conserved because there is no viscosity, no loss of energy, no friction is there. Basically. No resistance is there, not friction. No resistance is there. Energy is conserved. Now the question might come, what is hydrostatic law? So to calculate the pressure value, so I should write here between section 1, 1, 1, 2, sorry, not 1, 1, 1, should be 2, 2. So in this section whole, energy is conserved between them and hydrostatic law can be applied between them. Okay. Now 1, 1 means like this, 1, 2, 1 and 2, 2, 2. Now the question arises, what is hydrostatic law? So to measure the pressure when the at a particular point in the depth of the fluid, how will you get that from the hydrostatic law? Let us understand. Just give me a 2 minutes. Let's have a break. Then I'll join. Okay, so let's come back to the hydrostatic law. So it acts for both compressible and incompressible fluid, both ways. So suppose I have fluid like this fluid and it's at some depth. I consider a small fluid element here, a cylindrical small fluid element. This is a fluid element only. Okay. Fluid element. This is your data, sorry, reference. This is a reference point from here. We will follow the convention. When we are going below, we say that H is positive, and when we are going above, then our H will be negative. When we are going below, our pressure will be positive, and when we are going above, H will be negative. Okay. So this fluid element, suppose, is at a height of H height below. This will be positive H. The fluid element length is nothing but dH. Is dH. It has some weight W eventually. The fluid element has some weight W weight. Again, pressure is going to act at both the points above the fluid element and below the fluid element. So here the pressure will be PA. Sorry, pressure force. Pressure force will be P into A. Okay, this is your pressure force. And below also the pressure force will act. So it will be acting again normal to the surface. PA from the Taylor series expansion you can write dou P by dou A into dA. Okay. Sorry, dou P by dou H. Right. Because we are going vertically downwards. Dou P by dou H into dH into dA into dA. Sorry, A. A. Okay, or what I can say, I taken pressure will be like this from the Taylor series expansion into area. So P plus dou P by dou H dH A. So it is at rest, it is not moving. So net acceleration is zero. Net acceleration, that is in all the direction, AX I cap plus AY J cap plus AZ K cap. Oh, I should not write this because net acceleration AZ K cap is zero. All the components are zero. So net force is going to be zero on this. So as per Newton's second law, net force is mass into acceleration. So summation of net force is mass into acceleration, and this acceleration is zero. So net force is zero. This fluid element is at rest. So what is the net force acting? Net force is acting on the top layer and the bottom layer. The top layer is this direction, it is positive, and bottom layer is negative. So it is when you are going above, it is negative. When you are going below, it is positive, as from the conventions here. Okay, from the pressure conventions here. So this pressure is going up, that is why it is negative. This pressure is coming down, that is positive. Okay. So head forces in the vertical direction is PA plus weight is also acting below WD minus P plus dou P by dou H DH into A is equal to 0. So weight is how much? Specific gravity into volume, mgh. Okay. So this PA and PA cancels out. So PA plus specific 8 into specific weight, sorry, ADH, volume is ADH, minus PA, expand this bracket, dou P by dou H, DH into area is equal to 0. So this and this cancels out. You are left with W ADH is equal to dou P by dou H, DH into A. So DH cancels out. Now you are left with dou P by dou H is nothing but specific gravity, and this A and A also cancel out. That is nothing but specific weight as rho g. Dou P by dou S is rho g. And if you now, for an incompressible fluid, what you can say, dou P by dou H is the change of pressure with respect to height, okay, is nothing but your density into gravity. For incompressible fluid, for incompressible fluids, density doesn't vary. Okay, so density is not the function of pressure. That means dP is directly proportional to dH. dP will be done. Both are positive. Both are positive. All right. So let us do one scenario. Let us understand one scenario where we have, so same conventions we are going to follow. When we are going down, both pressure and height, H is going to be positive. When we are going up, the pressure and height both are negative, positive and negative. So suppose I have a scenario like this. This is your reference. There is a wall. This is your wall. Something like a dam scenario. Water reservoir is there. This has the atmosphere above and below. And suppose this is a point 1. And suppose you take a point 2 here. Point 2, which is H height below. Which is H height below. Again, our sign conventions are the same. H P negative and below H P. Now, this side of wall is experiencing a constant, right hand side of the wall is experiencing constant pressure because it's an empty. So the pressure on the right hand side of the wall from this situation I shall have used this. Pressure is going to act constant. That is P atmosphere. Okay. The right hand side of the wall is going to experience only P atmosphere. But here on this side, left hand side, this part is going to experience P atmosphere. This part is going to because it's above the water, okay, in the atmosphere. But the below part is going to experience some another pressure, that is increasing hydrostatic pressure. Okay, plus P atmosphere is also acting. Okay, what's happening? P atmosphere is acting. P atmosphere plus a hydrostatic pressure scenario as well, which is like this. Because of the presence of liquid. So this is maximum it will be because it is below 0.2 is at till here. So this is rho g h, because this was your nothing but pressure is rho into, as soon as you integrate it is rho g, dou p by dou h is rho g, so pressure is rho g h. This is your hydrostatic pressure at this low. I'll get that hydrostatic pressure value. I should not write here. I was just trying to explain, but let us understand. So we know that from the hydrostatic law, dp by dh is nothing but rho g. Okay, so integrate it. dp is equal to rho g into dh integrated. So pressure will be from point 1 to point 2, point 1 to point 2. Here also height will be from point 1 to point 2. So pressure at point 1 is P atmosphere. Pressure at point 1 is P atmosphere. And at point 2 it is, suppose let us say it is P. We don't know what is value. This is PP. And this is rho g. What is height at point 1? It is 0. And at height point 2 it is h. dh. Now integrated, it will be P minus P atmosphere is equal to rho g h minus 0. So pressure P is P atmosphere plus rho g h. P atmosphere. That is what I have done here. If you observe, so this is P atmosphere plus also rho g h. So left hand side of the wall is explaining P atmosphere plus the rho g h. Okay. So as soon as the height changes, rho g h1, h2, h3, till bottom it is h we have considered. And if, so this is your expression. If P atmosphere is 0, that means in the last session we have seen it is a gauge pressure. So it is P is nothing but rho g h. Gauge pressure. All right. So it means basically it's a linear function. It is linear. Increasing it. Understood? There is a wall and how the pressure is actually with the left hand side of the wall and the right side. So here pressure is P, which we don't. But finally we got the value as the rho gauge in the terms of gauge plus P atmosphere. Okay. Now this was a scenario for liquid. What will be scenario for gases? For gases. Density is a function of pressure and temperature for gases. Okay. Let us assume a isothermal case where temperature is constant. Okay. Let's assume isothermal scenario. Let's assume isothermal scenario. So again, I have a reference level here. The point here is 1. Okay, here h is 0. Then I have considered a point P here. Point P. Okay. And this height is till h height. Okay. Now, this is a gaseous scenario. This is not liquid. Okay, gaseous scenario. So what's going to happen? dP by dh is rho g, as we know that. Okay, but here rho is not constant. since the rho is function of P and T, since rho pressure is rho RT. Okay. So from here, rho you can put as RT by P. Therefore, dP by dH is RT by, sorry, P by RT. My bad. P by RT into G. Okay. So put the values here. So dP by P integrate is equal to G by RT pH integrate. So from P atmosphere to P value, here pressure is atmosphere, P atmosphere to P, 0 to H. So dP by P is integration is ln of P from P atmosphere to P is equal to GRT into H. So it will be ln of P by P atmosphere is equal to GH by RT. So from here, your pressure will be P atmosphere into e to the power of GH by RT. So that means an exponential function now. It's an exponential function. Okay. Multiplied with pressure. Okay. So if H is 0, then you can say that pressure is at e to the power of 0 is 1. So P is P atmosphere. If H is 0, this implies P is nothing but P atmosphere into e to the power of 0. That is P atmosphere. Okay. So how your plot will look like? There will be a constant pressure that is obviously the atmosphere. Okay. Also an exponential function of pressure will be there. So it will look something like this. Okay. So pressure is proportional to the e to the power of h. E to the power of h. Okay. For gases, the scenario is different. Okay. Any doubts still here? Anyone? Okay, no doubts. So what do we understood from so far? That hydrostatic pressure varies with the vertical depth. Okay, with the vertical depth, not any inclined depth or horizontal depth. So let me write here a note point. First point is, if I have liquid like this, and my point of consideration is this, where pressure is P, which is below height H, vertical height H. Suppose I also have an inclined height L, suppose like this. Okay, so pressure is, if it is asked that what is pressure value, it will be rho G H and not rho G L. Okay, not rho G L. Okay, so hydrostatic pressure varies in vertical depth. Okay, vertical depth. Another scenario, if I set up like an inclined plane tube manometer and vertical tube manometer, you will understand different kind of manometer, pressure measuring devices. Don't worry, but you might have seen in your laboratories, your mechanics laboratory, that there is a inclined plane manometer and vertical plane manometers are there. So suppose the setup is something like this. So this is an inclined plane manometer. And this is a scenario of vertical manometer. Okay. So liquid is there eventually, which is at equal height. Okay. Both are at same level. I think I've should looks like this. Okay. We don't know what is pressure here, so let us say it is pressure P. Okay. It is filled with liquid. This is your reference level. From this to this, it is height h. Okay. This is also height h, but this is height L. Oh, sorry. Then okay, this is length L. Now you need to get the value of pressure from both vertical as well as inclined plane. Okay. Let us see, does they give same reading or are different? So from a vertical, that is left hand side, your pressure is nothing but pressure P at the level is P atmosphere. Again, here it is P atmosphere. Here also it is P atmosphere. It is P atmosphere plus we are seeing from the vertical parameter that is rho GH. It is below height h. Okay, it is below height h. All right. Now from the other scenario, that is inclined plane manometer. So what we will say, it is P atmosphere, and as you go below, it will be a summation of some heights, summation of some vertical heights, not inclined lengths. So let me draw with another color. So vertical height from this point is suppose till here it is h1. So I'll go till this level, then I'll go vertical height. This is h2. So this is h1. This is h2. From here, this level I'll go till this point. This is h3. From here till this point I'll go. This is h4. Summation of all the vertical heights, not inclined heights. So from here, P is nothing but P atmosphere plus rho g h1 plus rho g h2 plus rho g h3. And I take rho g common out. And what is h1 plus h2 plus h3 plus h4 also? Plus h4. So h1 plus h2 plus h3 plus h4 is nothing but your total height. H. So again, both of them gives same value as the answer. So it doesn't matter. Okay, it doesn't matter. Both the manometers give you the same. I hope there are no doubts still here. Let's come to another topic of hydrostatic paradox. So there is a paradox. This hydrostatic paradox. So what does it say? Suppose you have a beaker of fluid. open to the atmosphere, open to the atmosphere, and it is filled with liquid. It is filled with liquid. So again, it is of height h, let us say. So pressure is nothing but acting here. That is your rho g capital H. And eventually there will be a force F at the bottom, Ft, because of the pressure. And the area of this is, bottom is A. Area is A. So what is Fp? Pressure into area. Pressure is rho gh into A. Or rho g can be written as specific weight into H into A. This is your pressure force. Okay, which is acting downwards. Acting downwards. Okay. Another scenario I have like this. Here I have a setup like this. Or I should set up like this. And a fluid is filled up till like here. Okay. This total height is h. Okay. The small height is also small h. This small a is area A. Area is A, and below has capital area. So this height will be how much? Capital H minus small h. Subtract from the total height, the smallest height. Okay. So there will be two pressures acting. One at this plate, one at this side, top side. Okay. So here again, pressures are acting. Pressures here are rho g capital H. Okay. And because of that, there is a pressure force Fp1. Okay. And here some pressure is acting. Okay. And here some force will be Fp2. Fp. And this is your reference. Okay. So what will be Fp1? Pressure force at 1 is pressure at 1 into area. And pressure at 1 is nothing but rho g capital H into area, which is acting downwards. What is pressure at 2? Pressure force at 2 is pressure at 2 into area is how much? Capital A minus small a. Okay. So this whole minus this is your area. And pressure at 2 is rho g, height is small h as per hydrostatic. A minus A. And this is acting upwards. So when pressure is acting upwards, we'll say it is negative. And downward it is positive. Okay. Now this liquid has a weight. That is nothing but weight of the liquid, which is acting downwards. This whole liquid W weight is acting downwards. Okay. So weight is specific weight into volume of this complete setup. W into total volume is the bottom side and the top side. So bottom side is this much and top side is this much, the liquid filled. Okay. So weight of the liquid filled is bottom side is capital A into H minus H plus small a into height H. So this is W into AH minus EH plus AH, that is W into AH minus A into, sorry, H into A minus A. Small a, because I have taken negative sign outside. Small a minus capital A. Okay. So net force is, and what is net force? FP1 minus FP2. So this is the force due to the weight of the liquid. Let us see that it is same or not. Okay. And F net due to liquid force is FP1 minus FP2. So FP1 was how much? WAH, and FP2 was WH into A minus A, right? From above these two. Rho G is WH, A minus A. So it is W take out common, AH minus H into A plus A into small h. Again it is W AH minus H into A minus A. Okay. Am I right? Capital A minus A. Here also capital A minus A. I have written mistake here. Okay. And this is also acting net force. And this net force is equal to weight. Equal to your. So hydrostatic pressure is independent of the weight of the liquid, whatever the weight of liquid is in the container. It depends only on the vertical depth. This vertical depth. Okay. Dependent only on the vertical depth of liquid and the surface areas. And the surface area. Okay. So I'll write a point here is that hydrostatic, whatever the weight, it's the pressure force is coming out to be equal to weight. Weight is nothing but your pressure force only. Hydrostatic pressure is independent of weight of liquid is independent of weight of liquid in container, and it depends on vertical depth of liquid and surface area. Okay. So suppose I have different kind of beakers of different shapes. Suppose my one shape is like this. Okay. Another shape is like this. Okay. Another shape is like this. Another shape is like this, suppose. Okay. All these are different kind of shapes with A, B, C, D, and all of them has different areas. This has area A1 at the bottom, A2, A3, A4. Okay. And all are filled with same liquid, And this is your suppose the reference level for all. Okay, and height is also same, that is capital H. So what is pressure force here? Fa is nothing but P into A 1. Okay, whatever P1 pressure is there will be same. It doesn't depend. Pressure is always same. Pressure is rho G into H. So pressure will be same and area is different. F at B is pressure into A2. F at C is pressure into A3, and F at D is pressure into A4. And what is the pressure values? In all these scenarios, in all these three, pressure is rho GH. Okay. But here, if I want to see what will be the pressure, so it will be looking something like this. You go from here, vertical depth. Again, you go from here, vertical depth. Go from here. So this is H1, H2, H3. So pressure here is rho G H1 plus H2 plus H3, and this is eventually nothing but your rho GH only. H1 plus H2 plus H3 is rho GH. So weight of the liquid in container is nothing but net vertical force by the fluid on the container. So weight of the liquid is nothing but net vertical force. Okay. All right. Let us write the weight of liquid in container is net vertical downward force by the fluid on container. I mean net vertical force. Okay. So suppose you have a scenario like this, a beaker is like this, of this kind of shape. Okay. This is a point A, this is a point B. Fluid is filled. This is a reference from here till here. Pressure force is going to act on this. Okay. And net pressure force is going to count FP. Also, there is weight of the liquid. Weight of this of the liquid. So your net vertical forces weight. Net vertical force, V for vertical. Okay. Let's take a short 2 minutes of break and we'll rejoin. Okay, let's come back. Now the next topic is conversion of one liquid column to another. Conversion of one liquid column to another, or you can say equivalent fluid column. So what do I mean by this is that suppose you have a beaker which contains a fluid up till suppose height h, and this liquid has a density rho1, and the height of the liquid is h1. Now, if I have another beaker with some another liquid, if I have another beaker and density is rho2 and the height is h2. H2 is your height. So if suppose density of fluid 1 is, if density of fluid 1 is greater than density of 2, then for pressure to be equal in both of them, and for the pressure to be equal in both of them, what I mean, pressure at this point and this point, if you want the pressure to be equivalent P, then for pressure to be equal, your height h2 will be different from h1. Your height will be different in both the scenarios. Since here your pressure is rho g h1 and here your pressure is rho g h2, rho 2g, rho 1g. Okay, so that means this implies rho 1 g h1 is equal to rho 2 g h2. G cancels out, and since rho 1 by rho 2 is equal to h2 by h1, and this ratio is greater than 1, so that means h2 is greater than h1. H2 should be greater than, sorry, rho 1 by rho 2, and I said that if rho 1 is density is greater than rho 2. So for same pressure to be equal, the ratio will be like this: rho 1 by rho 2 is h2 by h1, h2 by h1. So this implies h2 will come out to be rho 1 by rho 2 into h1. So for pressure P to be equal, your h1 should be greater than h2. Height in the first should be greater than height in the second, or height in the second should be less than height in the first, whatever you can say. Okay. For pressures to be, so that means rho 1 h1 is equal to rho 2 h2. Rho 1 can be written in terms of specific gravity as well. So that can be written as rho 1 by rho 1 of water into h1 is equal to rho 2 by rho 2 of water into h2. So it can be specific gravity of 1 into h1 is equal to specific gravity 2 into h2. All right. So if and specific gravity suppose of 2 is water. Example, if S2 is 1, that is water you are taking, then what will be your H2? It will be S1 into H1. Specific gravity of the fluid 1 into the height of. Similarly, you can write this in terms of specific weights as well. H2 in terms of specific weights, or specific, if you multiply with G, so it will be rho 1 by H1 by, or W and by H1 by. So let us take an example here that there is this example again. So this is a fluid, water. Okay, your fluid 1, and this is, you don't know what fluid it is. Let us say this is a height 2, H2, this is H1 height. Okay. And let us say it is mercury. So H1, suppose it is 1 meter. This is 1 meter of water column. You don't know what is H2. And this is your mercury, Hg. So for pressure to be same, rho of water into H of water is equal to rho of mercury into H of mercury. What is rho of water? In terms of specific gravity, I can write. Let's tell you. Specific gravities. So it is 1 into 1 is equal to specific gravity of Hg into rho of Hg. Since you know that specific gravity of Hg is 13.6, so it is 13.6 into H of Hg is equal to 1. Okay. So your water column, or if I say instead, let's take an opposite way. This is you don't know, and this is 1 meter. Let us say for 1 meter of mercury column, how much of liquid column, water column you need? Okay, let us do in that scenario. So it will be H of water, you don't know, but this is 1. So H of water will be 13.6 times higher. Okay, 13.6 meters of water column you need. If you want to have a pressure measuring device with the water, then it should be 13.6 times of length compared to that of mercury. So if you have seen in your laboratories, you have seen that there is mercury is used. So with 1 meter of mercury only, we can get the atmospheric pressures compared to the water column. That's why we don't put water, because the tube will be so long. Okay. Now, next point is that suppose if I have a scenario like this again, at till point P here, I don't know what is pressure. This is a height H, and P atmosphere, suppose it is 0. Okay. So this P will be rho G H. So P is nothing but your specific weight into H. So H is P by specific weight. So what I'm trying to say here is that the unit of pressure can also be expressed in terms of head of the column. This head H. This implies the unit of pressure can also be expressed in terms of head of liquid column, whatever is the specific weight, rho density value. It depends on that. Now, next is units of pressure. What are units of pressure? Different units of pressure. So again, SI units. So pressure is nothing but Newton per meter square, or it is said as pascals. Pascal. Okay. So what is kilo in terms of kilopascal? I'll multiply with both sides Newton per meter square, and it will be 1 kilopascal. Okay. If I multiply with 10 to the power of 6 Newton per meter square, it is 1 megapascal. Okay. 1 megapascal. Also, P atmosphere is, you know that it is 1.101.325 kilopascals. Or you can write 1.01325 into 10 to the power of 5 pascals. 1 bar is nothing but 10 to the power of 5 pascals. So P atmosphere can be equivalent to 1.01325 bars. Or you can write 1 bar. Okay. P atmosphere is either 1 bar or 10 to the power of 5 pascals. Okay. Also, in terms of kgf, 1 kgf is nothing but 9.81 newtons. Okay. So kgf per centimeter square, if I say 9.81 Newton per centimeter square. Okay. So if you want to convert it into meter square, then you have to multiply with 10 to the power of 4 Newton per meter square. So that is again 10 to the power of 5 Newton per meter square. And what is Newton per meter square? It is Pascal. 10 to the power of 5 Pascal. So therefore, 1 kgf per centimeter square is 10 to the power of 5 pascals, or 1 bar, or 1. It is a metric system. Also, in terms of torque, it is also defined. There is a barometer, which is a atmospheric pressure measuring device. It was defined by Torrivelli. Okay, designed by Torrivelli. So that's why the unit is torque. So for a barometer, suppose you have a barometer of like this. Barometer is nothing but a tube dipped in liquid. Liquid is nothing but your mercury, because we can't have a lengthy tubes. So this is P atmosphere acting. Okay, least count is, suppose least count is 1 mm. LC is 1 mm. Okay. And this liquid is mercury. This is the barometer. Okay. So 1 mm of Hg, that is your least count also of the mercury, is 1 torr. So 1 torr is 10 to the power of 3 minus 3 meter of mercury. Of mercury. 10 to the power of, in terms of head we are saying, because I wrote in the note. Okay. Meter of mercury. So it is 13.6 into 9810 meter of mercury converted into pascals. So 1 torr is 133.33 pascals. How I got? Since pressure is specific weight into Hg. Pressure is W H of H is 1, 10 to the power of minus 3. And specific weight is 13.6, rho g 9.8. Now in terms of pound force if I want, PSI, that is LBF per inch square. So it is FPS system, that is foot pound second. FPS system, foot pound second, FPS system. Okay, FPS system. So 1 LBF is nothing but 0.453 kgf. And you know that 1 kgf is 9.81 Newton. So 0.453 into 9.81, it will be in terms of Newton. Okay, and 1 inch is 2.54 centimeters, and in meters it will be 2.54 into 10 to the power of minus 2 meters. So 1, and you know that 1 LBF in terms of PSI, it will be, if you just divide LBF by inch square, it will come out to be 14.69. 14.69. All right. Now the next thing towards the end. So if you want to measure the atmospheric pressure, so the atmospheric pressure by the environmental mass on Earth's surface is known as the atmospheric. The pressure exerted by the pressure. What is atmospheric pressure? The pressure exerted by the environmental mass on Earth's surface is known as environmental or atmospheric pressure. Okay. So if you want to measure through manometers or barometers, so liquid column with the water, as we have seen, will be 13.6 times higher with compared to that of air. So suppose this is your Earth. Okay. So P atmosphere here, and this is the total amount of air, suppose, in the on the Earth. So P atmosphere here will be 101.325 kilopascal. To measure using a equivalent system using water or mercury. So one scenario is like this, and one scenario of Earth is like this. So either you can make a system like very heighted system compared to a small heighted system of mercury. So this will be height of water, and this will be height of mercury if you use mercury as a fluid. Okay. That is why, as we have calculated, so here both will have P atmosphere eventually. But with a smaller height we can have. So you can say that specific weight of water into H of water is your P atmosphere here. It is 9810. H of water is 101.325 into 10 to the power of 3. So H of water is 10.3 meter of water column you need. So it's more than a height of an electrical pole which you have in your streets. Okay. Whereas here, specific weight of mercury into H of mercury is P atmosphere. So it will be H of Hg will be 760 mm of Hg column. That is 76 centimeter of Hg column. It's very small height, 76 centimeter, point even less than a meter. That is why manometers of mercury are used to measure the atmospheric as an equivalent system of air in mercury. Equivalent system. Okay, so we'll end up the session here. And I hope if anyone of you has missed, you can go back and check the tutorials videos, any of the lecture videos. So all of them are uploaded on my YouTube channel. All these video recordings are uploaded on my YouTube channel. My YouTube channel name is NPTEL with Varnit. So there you will find all the lecture notes PDF, all the videos, and in all the videos description, there will be the link to the Google Drive for all these PDFs. As well as NPTEL team will also send you the feedback form where the recording sheet is there. Those who have registered and enrolled in the course, they will get the mail from the NPTEL. And there you can see all the recording sheet. All of the TAs are there. So my name is Varnit Kapoor, and the name will be there. You can check out my lecture videos if you are attending from the start. So this is it for our session, and I'll see you hopefully in the coming week, or maybe there can be a chance that next week there might be a delay. Next week there might not be a tutorial. Possibly, I need to. I have to go somewhere, so it will be next week. Two continuous back-to-back tutorials. You'll get the mail from the NPTEL team as per my schedule. Okay. So thank you. I think we can stop here. If anyone has any doubts, I'll be here. You can ask.